Could two universes have the same kind of space and still be different universes? It sounds impossible because if the geometry is the same, what could still be different? But cosmology separates those questions. Two models can share flat spatial curvature while containing different mixtures of matter, radiation, and dark energy, producing different expansion histories. Planck's final full mission analysis offers the first clue. It found good consistency with a spatially flat model that still required 6 baseline parameters. So tonight's question is how much of a universe the geometry of space can actually tell us. Those 6 parameters show where the distinction begins. The baseline model fixes the curvature class while still seeding separate information about ordinary matter, dark matter, the primordial fluctuations from which later structure grew, and quantities connected with the expansion and the microwave background. Flatness, therefore, does not replace the rest of cosmology. It is one constraint inside a model that still has to identify the physical contents and the history they produce. The words space and universe often travel together so closely that they begin to sound interchangeable. In ordinary conversation, they almost are, with space used for where the stars are and universe used for everything out there. We pass over the difference because most of the time, nothing seems to depend on it. But in cosmology, the distinction matters, and it matters for a surprisingly gentle reason. A description of space tells you something about geometry. A description of a universe has to tell you more than that. It has to tell you what exists within that geometry, how the distances between things change, and what story those changes belong to. A measurement gives us a cleaner starting point than an abstract definition. In the last few decades, cosmologists have built increasingly precise pictures of the large-scale universe by studying ancient light that began its journey when the cosmos was very young. That light, known as the cosmic microwave background, reaches us from a time long before stars like the sun existed. It is faint, cool, and almost perfectly uniform, but not completely. Across it are tiny variations, delicate changes in temperature that carry information about the early universe. By measuring those patterns with extraordinary care, missions such as Planck helped cosmologists test what kind of large-scale geometry best describes the observable universe. And one of the most important results was that the standard spatially flat baseline model fits the observations well. It is also worth being careful with the word flat. Observations can constrain curvature very tightly without turning a measured uncertainty into mathematical proof that curvature is exactly zero. For this discussion, the important point is not exactness to an infinite number of decimal places. It is that even if we grant perfect flatness as a thought experiment, the cosmological model is still not uniquely determined. The question survives even after the geometric uncertainty is removed. A curvature constraint is also an inference made inside a model, not a view of the universe from somewhere outside it. Planck measured correlations in the microwave sky and compared their angular pattern with theoretical predictions. The fit can strongly prefer a narrow range of curvature, while other parameters remain free to move within their own allowed ranges. That is ordinary scientific inference, and it is exactly why one very precise result can coexist with several other quantities that still need to be measured. That phrase sounds simple, perhaps simpler than it really is. A flat universe does not mean a universe that looks like a sheet of Pepsi. It does not mean a cosmic floor, or a giant plane with an edge somewhere beyond the galaxies. Flat, in this setting, means something more quiet and more precise. It refers to spatial geometry on the largest scales, to the way lines behave, the way distances add up, the way triangles would work if you could draw them across immense reaches of the cosmos. If that sounds almost mathematical, that is because it is. But the mathematics is only the careful version of an intuition we already have. We know what flat means in a room. We know that parallel lines on the floor do not meet. We know that the angles of a triangle drawn on a flat surface add up in a familiar way. Cosmology asks whether the same broad logic holds when the surface is no longer a floor, but the fabric of space itself, stretched across the largest distances we can observe. Planck's final CMB analysis and standard combined fits are consistent with large-scale geometry being very close to flat. At first, that can sound like the whole story. If cosmologists can identify the geometry on the largest scales, perhaps the universe itself has been identified. The difficulty is that curvature occupies only one place in a cosmological description. Other entries specify the matter content, radiation, dark matter, the behavior assigned to dark energy, the initial pattern of fluctuations, and the rate at which the cosmic scale changes. Two models can agree on curvature, while disagreeing on several of those other entries, and once they do, they need not share the same history. This is easier to follow if we treat geometry as one measured property rather than as a synonym for the entire cosmos. A universe has spatial relationships at any chosen epoch, but it also has physical contents and a rule for how those contents evolve. Knowing the first part can be extraordinarily informative without determining the others. Imagine, just for a moment, that you could freeze the cosmos at a single instant. Every galaxy would pause where it is. Every beam of light would be suspended in motion. Every cluster and every dark gap would be held perfectly still. Then imagine that, in this stillness, you could measure spatial geometry itself. You could determine whether that space was positively curved, negatively curved, or flat. You would have achieved something astonishing. You would know an immense amount. And yet, even after all of that, you still would not know everything needed to identify the universe before you. From geometry alone, you would still not know how much matter the model contains, how important radiation was at earlier times, the instantaneous expansion rate at the epoch you selected, or which late-time component is influencing that change. The geometric result would be correct, but it would leave much of the dynamical description open. So the opening question is a real cosmological distinction rather than a word game. Can two universes share the same flat curvature? Yes, in the specific sense that both can belong to the flat curvature class, while still differing in their contents, their balance of ingredients, and therefore in the way they evolve. One might be more strongly shaped by matter, another by radiation in an earlier age, another by the slow dominance of dark energy. The geometry alone does not tell the whole tale. The distinction becomes clearer when we ask exactly what a measurement has established. A result about curvature answers a geometric question. A cosmological model has to carry additional information about contents and evolution, and the rest of the night will follow the consequences of that difference, rather than treating the two words as interchangeable. This also keeps the argument from depending on a verbal definition of universe. The distinction can be tested inside the equations by holding the curvature term fixed, altering the component densities or pressures, and checking whether the predicted expansion changes. If it does, then the shared geometric property was never sufficient to identify the full model. That is the experiment we will repeat in several different forms. For now, it is enough to keep one calm limitation in mind. If an observation tells us that large-scale space is consistent with flat geometry, it has given us a real piece of the universe, but it has not yet told us which complete cosmological history that geometry belongs to. So when cosmologists say the observable universe appears spatially flat, they are telling us something very important, but not everything. They are telling us about cosmic curvature on the largest scales. They are not, by that fact alone, telling us the full content of reality, the balance of its ingredients, or the complete story of how this universe has changed from its earliest light to the long future ahead. That quiet incompleteness is where our question begins. Because if flatness is not enough, then the next thing we need to understand is what flatness actually means, and why a piece of geometry that sounds so simple can still leave so much undecided. So let us move there slowly now, and look more carefully at what cosmologists mean when they say that space is flat at all. When cosmologists say that space is flat, the word flat is doing a very different job from the one it does when you place a book on a table. There is no suggestion that the universe is a thin surface, or that everything we see has somehow been pressed into two dimensions. The word refers instead to geometry, to the rules that connect distances, directions, and angles when you move through space. In the standard cosmological picture, a spatially flat universe is one whose large-scale geometry follows the familiar Euclidean rules we learn from ordinary flat surfaces. It is also the geometry assumed in the standard spatially flat lambda CDM model that fits the Planck observations so well. There is a simple way to feel what that means without needing an equation. Imagine drawing a triangle on a large sheet of paper. You choose 3 points, connect them with straight lines, and then measure the 3 interior angles. Add them together and you get 180 degrees. You could draw larger and larger triangles, and as long as the surface remains flat and the lines remain straight, the same rule continues to work. Now imagine trying something similar on the surface of a sphere. The surface of Earth is curved, although across a small patch of ground it appears almost perfectly flat. If you travel far enough, however, the curvature stops being negligible. Lines that behaved one way on a sheet of paper can behave differently on the sphere, and triangles built from the straightest possible routes across that curved surface can have angles that add up to more than the flat space total. The geometry has changed, even though someone living on a tiny patch of the surface might not notice immediately. The spherical example gives the mind something familiar to hold, while the actual cosmological idea remains much harder to picture. There is another possibility as well. A surface can curve in the opposite sense, something often compared with the shape of a saddle. On that kind of geometry, triangles can have angles adding to less than the flat space total. So even with only these three broad possibilities, we already have three different sets of geometric behavior. Positive curvature bends one way, negative curvature bends the other, and zero curvature gives the familiar flat geometry in between. The analogy is useful, but it has a limit that is worth keeping clear. A sphere or a saddle is a two-dimensional surface that we can imagine sitting inside a larger three-dimensional room. Cosmological space does not need to be pictured that way. When physicists talk about the curvature of three-dimensional space, they do not need to imagine our universe bending into some larger visible room outside it. Curvature can be described from within the geometry itself, by asking how distances, angles, and paths behave. That is a very quiet change in perspective. You do not have to stand outside a sphere to discover that its surface is curved. You could remain on the surface and make measurements, travel far enough, construct large enough figures, compare distances carefully enough, and the geometry begins to reveal itself from the inside. Cosmology does something conceptually similar, although the real measurements are far more sophisticated than drawing enormous triangles among the galaxies. The light that reaches us from the early universe carries patterns with characteristic angular scales. Planck measured those patterns across the microwave sky with extraordinary precision, and the final Planck analysis found strong consistency with the standard 6-parameter cosmological model in which the large-scale spatial geometry is flat. In that final analysis, the characteristic angular acoustic scale was measured with extraordinary precision, which is one reason the microwave pattern can put such strong pressure on models that alter the geometry. Planck's analysis also shows why the word flat should be handled carefully. It is part of a model that contains several independent cosmological parameters. Flatness does not arrive alone and somehow specify everything else. That distinction is the doorway we need. Suppose you somehow learned with perfect certainty that the large-scale spatial geometry of a universe was flat. You would now know something profound about the way measurements work across that space. You would know the curvature class. You would know that on the relevant large scales, its geometry behaves like the Euclidean case, rather than the positively or negatively curved alternatives. But you still would not know how much ordinary matter exists there. You would not yet know the dark matter density. You would not know the detailed history of its expansion. And you would not know which mixture of cosmic ingredients had produced the universe you were observing. The Planck cosmological model makes this separation unusually easy to see because spatial flatness is assumed in the baseline model while other quantities are still independently measured, including the densities of ordinary matter and dark matter, the parameters describing primordial fluctuations, and quantities related to the later expansion of the universe. A single geometric statement does not replace those other measurements. So we can make our frozen universe thought experiment a little more precise. Imagine again that all cosmic motion has been paused. Galaxies hang silently in place. Light no longer crosses the darkness. Nothing evolves while you take as long as you need to measure the spatial geometry. Eventually you complete the impossible survey, and the result comes back as flat. That answer tells you how the spatial relationships behave. Now remove every physical label from the description. Do not tell yourself which points are galaxies, how massive they are, how much invisible matter surrounds them, or how much radiation fills the universe. Do not allow yourself any information about how quickly the distances between large structures were changing before the freeze. You have retained the geometry, but much of the universe has disappeared from your description. And the strange thing is that the geometry has not become false. It remains useful and physically meaningful, but it supplies only part of the description. This is easier to understand if we imagine two coordinate grids drawn on transparent sheets. On the first sheet, the geometric grid is perfectly flat. On the second sheet, the geometric grid is also perfectly flat. If geometry were the only information that mattered, the two sheets would tell the same cosmic story. But now begin adding what actually occupies them. Give one model a certain balance of matter and radiation, give another a different balance of cosmic components while preserving shared spatial curvature. Once time is allowed to run, the two models do not have to evolve in the same way. Their common flatness has not forced their histories to match. This is the distinction we need. Two cosmological models can belong to a shared spatial curvature class without becoming the same cosmological model. The word flat identifies an important property of their geometry, while the word universe must carry the additional physical information that makes each evolving cosmos what it is. There is one more subtlety here, and it helps prevent a common picture from settling too firmly in the mind. When you hear flat universe, you may instinctively imagine the cosmos viewed from far away, perhaps as an enormous glowing disk floating against a black background. But the word is not describing an external silhouette. It is describing internal geometric relationships. If the universe is spatially flat on large scales, there does not need to be some observer outside it who can look back and see that flatness as a shape. The geometry is something inhabitants can infer while remaining inside. That is part of what makes cosmology so unusual. We do not get to step away from the object we are studying. We cannot put the universe on a table, walk around it, and inspect the other side. Every telescope, every detector, every measurement has always been made from somewhere within the thing being measured. Even from inside the system, geometry leaves measurable traces in the way ancient light reaches us, in the angular patterns preserved across the microwave sky, and in how measured distances depend on cosmic expansion. By comparing those traces, cosmologists can ask which geometry best fits the observations, without requiring an imaginary vantage point outside the universe. Planck's final results found that the familiar spatially flat lambda CDM model provides an excellent fit to the cosmic microwave background data, and combining the early universe information with later distance measurements constrains the geometry more tightly. But even this successful model needs more than curvature. The baseline description contains multiple parameters because the universe cannot be reconstructed from geometry alone. Return for a moment to the two transparent coordinate grids. Their curvature can be identical, so both obey the same flat geometric rules, while the physical quantities written over those grids differ. Once the models are allowed to evolve, those differences in contents can alter the expansion, even though the curvature classification remains unchanged. To discover that, we need more than curvature alone. We need something that has been traveling through the universe for almost its entire observable history, carrying a record of conditions from a time when there were no galaxies like the Milky Way and no stars like the Sun. That record is the microwave background, and when we look more closely at the patterns inside that ancient light, geometry stops being an abstract idea and becomes something the universe has actually allowed us to measure. That ancient light is useful because it comes from a much simpler early state of the cosmos. The microwave background began traveling freely at an age of roughly 380,000 years. Before that time, the cosmos was filled with a hot plasma of charged particles. Light could not travel very far without interacting with them, so the early universe was opaque in something like the way the interior of a dense fog is opaque. As the universe expanded, it cooled. Electrons could finally remain bound to atomic nuclei, the plasma became neutral gas, and photons were able to move through space without constantly being scattered. Those photons have been traveling ever since, while cosmic expansion stretched their wavelengths until radiation from a much hotter young cosmos now reaches us mainly as microwaves. Measurements that include the COBE-virus data place the mean temperature today at about 2.7 Kelvin, and the sky is almost uniform, but not perfectly so, which is precisely why it carries so much information about the early universe. Across the microwave sky are extremely small differences in temperature. One direction may be slightly warmer than another slightly cooler, and those variations correspond to differences in the density of the early universe. They are tiny, but they matter enormously because the structures we see around us today grew from those early irregularities. When this light began traveling, the Milky Way and the Sun did not yet exist, nor did Earth or the familiar pattern of mature galaxies spread across the present sky. The young cosmos was still near the beginning of the long process by which small density differences would grow into stars, galaxies, clusters, and planets. When a mission such as Planck maps the microwave background, it is measuring a very old pattern rather than treating the sky as a simple photograph. It is measuring a pattern that was created before nearly all of the large structures in the present universe existed. And inside that pattern is information about geometry. This can sound mysterious at first. A patch of slightly warmer microwave light does not seem like something that should tell you whether cosmic space is flat or curved. But the connection becomes easier once we think about what produced those patches. In the young universe, matter and radiation were not distributed with perfect uniformity. Some regions were slightly denser than others. Gravity tried to pull matter into those denser regions, while the pressure of the hot photon-filled plasma resisted that compression. The result was an oscillation in which a region could begin to compress under gravity while pressure pushed back, allowing waves to travel through the early plasma. Physicists call these acoustic oscillations because the underlying mathematics has something in common with the way pressure waves travel through ordinary materials. They were not sounds that a person could have stood somewhere and heard. There were no ears, no air in the ordinary sense, and no quiet room waiting inside the young universe. The word acoustic refers to the behavior of the waves, to alternating compression and rarefaction moving through the plasma. Those waves had a limited amount of time to travel before the universe cooled enough for light to escape freely. That matters because it creates a characteristic physical scale. There was a maximum distance that these pressure waves could have traveled through the plasma by the time the microwave background was released. You can think of it as a kind of cosmic measuring rod left behind in the pattern of the ancient light. We know approximately how large that ruler should have been under a given cosmological model. We can then compare that predicted physical scale with the angle it covers on the sky, and the relationship between the two carries information about the geometry through which the light traveled. This is where the triangle we imagined earlier returns, but in a more useful form. Suppose you know the actual size of a distant object. If you also measure how large it appears to you, then the relationship between its true size and its apparent size contains information about the geometry between you and the object. On a flat geometry, that relationship behaves one way. On a positively curved geometry, the same physical ruler can appear at a different angular size. On a negatively curved geometry, it changes in the opposite direction. So instead of somehow leaving the universe and looking back at its overall shape, cosmologists can use a known physical scale imprinted in ancient light and ask how large that scale appears from where we are now. The universe has given us the ruler and the view of the ruler at the same time. The ruler itself is not independent of the rest of the cosmological model. Its physical length in the young plasma depends on the expansion rate before the microwave background was released, and on the densities that controlled the sound speed and gravitational response of that plasma. The apparent angle then depends on the distance the photons have traveled through the later universe. Cosmologists therefore fit these pieces together, rather than reading curvature from one isolated mark on the sky. The geometry is constrained because the early ruler and the later distance have to be mutually consistent. The ruler is usually called the sound horizon at last scattering. What the telescope measures most directly is an angle, while the physical scale of the sound horizon is inferred from the physics of the early plasma. The observed angular size depends on both the ruler itself and the distance over which its light has traveled, so the inference is never just a matter of reading curvature from one isolated mark on the sky. This is where the idea of a parameter degeneracy becomes concrete. Different combinations of cosmological parameters can sometimes preserve nearly the same angular scale, even while the underlying model changes. Matter densities influence the early sound horizon, while the later expansion influences the distance to the last scattering surface. A change on one side of that ratio can partly compensate for a change on the other. The microwave background therefore constrains geometry extraordinarily well within a model, but it also shows why cosmologists combine early universe measurements with later distance information. The relative heights of the acoustic peaks add another layer. Ordinary baryonic matter changes the balance between compressions and rarefactions in the early plasma, while dark matter influences the gravitational wells in which those oscillations occur. Those effects help separate quantities that curvature alone cannot determine. The microwave sky is especially informative because it carries several pieces of the model at once. While one geometric number does not contain the rest of cosmology, the nut carries 5 hadral pieces. Of course, reality is more complicated than a single ruler drawn across a simple background. The microwave sky contains an entire spectrum of fluctuations at different angular scales. Cosmologists analyze how strong the temperature variations are at one scale, then another, and the result forms a pattern of peaks and valleys known as the angular power spectrum. Those peaks are not decorative features in a graph. Their positions and relative heights carry information about different parts of the cosmological model. The characteristic angular scale associated with the earliest acoustic pattern helps constrain spatial geometry. The heights and relationships among the peaks also constrain the contents of the universe, including ordinary matter and dark matter, because different cosmic ingredients influence the behavior of the early plasma in different ways. This is already an important clue for our larger question. The same ancient light helps cosmologists study geometry and composition, but those are different pieces of information. Flatness does not automatically tell us how much matter there is. Matter density does not automatically tell us the primordial fluctuation spectrum. One observation contains several kinds of evidence, and the cosmological model has to bring those pieces together. Planck was designed to measure the microwave background with enough precision to tighten many of those constraints at once. Its maps covered the full sky, allowing researchers to compare the measured pattern with theoretical models and determine which combinations of cosmological parameters best reproduce what we actually observe. The result is the familiar baseline model called lambda CDM. The letters CDM stand for cold dark matter. Lambda refers to the cosmological constant used in the standard model to describe dark energy. In the baseline Planck model, the geometry at large scales is flat. The name already hints at how much more the model contains than curvature. Cold dark matter and ordinary matter have to be accounted for, the primordial fluctuations have to be described, and the later expansion has to be fitted together with the component represented by lambda. Flat geometry is one assumption inside that larger set rather than a substitute for the other parameters. That is why this ancient radiation is so useful for the question we are following tonight. It gives us a concrete example of the difference between learning about space and learning about the universe. If all Planck had done was establish which broad spatial geometry fits the observations, we would already know something remarkable. But cosmologists wanted far more than that, because a geometric answer by itself does not tell us why the microwave sky has the detailed pattern that it does. The pattern depends on what the universe contains. If the amount of ordinary matter changes while other assumptions are held fixed, the acoustic pattern responds. Dark matter changes other parts of the pattern, and a different expansion history changes the relation between the last scattering surface and the universe observed today. The microwave background therefore carries several kinds of information at once. To ask which model reproduce the whole pattern coherent print. To ask which these models can reproduce they combine. This is why cosmological measurements are rarely about discovering one isolated number and declaring the universe solved. A measurement constrains one family of possibilities. Another measurement cuts away some of what remains. A third can break a degeneracy, which is the name physicists use when different combinations of model parameters can produce effects that look too similar in one particular observation. That idea of degeneracy will become important later, because it points directly at the danger of trying to identify a whole universe from one property. For the moment, though, we can stay with the ancient light. Suppose two theoretical universes are both spatially flat. At the level of curvature, they belong to the same class. If curvature were all we measured, we might be tempted to regard them as variations of the same cosmic picture. But let one contain a different balance of matter and dark energy. Let one pass through its history with matter dominating for longer. Let another enter a period dominated by dark energy earlier. The geometry can remain spatially flat while the expansion histories separate. Distances between galaxies do not have to evolve in the same way. The growth of structure does not have to proceed in the same way. Their long-term futures need not look the same. And because the microwave background carries evidence about several parts of the model at once, cosmologists do not stop when one piece appears to fit. They ask whether the whole pattern can be explained coherently. There is something almost comforting about that method. Cosmology deals with scales so large that they easily become abstract. Billions of light years, ancient radiation, invisible dark matter, cosmic expansion. It would be easy for the subject to drift into pure speculation. But the actual work keeps returning to measurement. A pattern appears on a detector, its strength changes with angular scale, and competing models predict slightly different arrangements of those peaks, so the observations gradually decide which possibilities remain viable. Even the grand question of cosmic geometry is approached through this patient accumulation of evidence rather than through a photograph of the universe from somewhere outside it. We are inside the system, looking backward in time, using light that has crossed nearly the whole observable history of the cosmos to infer how space behaves on scales we can never physically survey with a ruler. And once you see how that inference works, the phrase spatially flat begins to feel less like a vague description and more like a measured property. But it also begins to feel narrower, because every step in the analysis reminds us that geometry is only one line in the description. The ancient light carries much more information than a curvature label. It contains information about matter. It contains information about the initial fluctuations from which galaxies later grew. It contains information that can be combined with measurements of the later universe. It gives us a starting point for reconstructing cosmic history. And the history matters because the universe we see tonight is not the universe that released that light. The young cosmos was hotter, radiation played a much larger dynamical role, mature galaxies had not yet formed, and the structures we observe today had not yet developed. What reaches us now is evidence from an earlier state of the same universe, separated from the present by billions of years of evolution. So if we want to understand why two universes with shared spatial geometry can nevertheless become profoundly different, we have to stop treating the universe as a single static geometric description. We have to let time back into the picture. Imagine placing the flat coordinate grid beneath the microwave sky, and then adding the physical quantities that the grid by itself did not contain, including the early plasma, matter, radiation, dark matter, and the small density variations from which structure can grow. Once the model is allowed to evolve, the problem changes from a static question about curvature into a dynamical question about how those ingredients shape the expansion. We are no longer asking only what shape the space has. We are asking what the contents of that space cause the cosmos to do. That is where the distinction becomes much easier to see, because the geometry may remain in the same broad class while the behavior of the universe changes around it. The microwave background has given us an early record and one of the rulers encoded within it. The next question is what that early record cannot decide on its own. If flatness describes the geometry, what remains unspecified? Quite a lot, as it turns out, because two universes can begin with the same broad kind of spatial geometry and still carry different mixtures of the ingredients that determine how their histories unfold. Quite a lot remains unspecified once you know that space is flat, because flatness tells you about curvature, while the evolution of a cosmological model depends on what fills that space, and on how those different ingredients respond during cosmic expansion. There is a useful word cosmologists use for keeping track of that expansion. They call it the scale factor. You can think of this quantity as a way of comparing cosmic distances at different times. If two galaxies are carried apart by the general expansion of the universe, the scale factor gives us a convenient way to describe how the large-scale distance between them has changed. It does not mean that galaxies themselves are swelling like balloons, And it does not mean that every object becomes larger. Bound systems, such as stars, planets, and galaxies, are governed locally by forces that hold them together. The scale factor describes the large-scale expansion of the cosmological background. Once that idea is in place, something interesting happens. Different components respond differently as cosmic expansion proceeds. Imagine a fixed collection of ordinary matter spread through a very large region. As that cosmic scale grows, the same matter occupies a larger volume and its average density falls. The familiar intuition is that increasing three-dimensional volume spreads a fixed collection of particles more thinly, and non-relativistic matter follows that broad behavior in cosmology. Matter therefore becomes diluted as the available volume increases. Its density falls with the cube of that scale, which follows from three-dimensional volume growing as length grows. Radiation becomes dilute for the same volumetric reason, but photons also lose energy as expansion stretches their wavelengths. But photons carry energy in their wavelength, and cosmic expansion stretches those wavelengths. A stretched photon has less energy than it had before. So radiation loses energy density in two ways at once. There are fewer photons per unit volume, and each photon is carrying less energy. Radiation energy density therefore falls faster than matter density during cosmic expansion. In the standard cosmological description, matter density falls with the cube of the cosmic scale, while radiation density falls with its fourth power. That difference sounds like a small mathematical detail until you allow the clock to run for billions of years. Then it becomes a history. Go far enough into the past and the scale factor was much smaller. Radiation density rises more rapidly as you trace the expansion backward, so there was an early period when radiation was far more important to the overall dynamics of the universe than it is today. Later, as expansion continued, radiation faded in relative importance more quickly than matter. Matter then became the dominant contribution for a long stretch of cosmic history. And much later still, another component became increasingly important. In the standard lambda CDM model, that component is associated with the cosmological constant, the lambda in the name of the model. Its behavior is very different from matter and radiation. In the simplest cosmological constant description, its energy density does not dilute during cosmic expansion. So while matter becomes thinner and radiation becomes thinner even faster, lambda's energy density remains constant. This means that the importance of the different ingredients changes even if none of the basic rules change. The universe can begin in one regime and gradually move into another because the components scale differently as cosmic distances grow. That is a remarkably economical way for a universe to acquire a complicated history. Nothing has to suddenly appear in the middle of the story. The ingredients can already be present, while their relative influence changes naturally with expansion. The relative balance therefore shifts with time. Radiation is most important very early. Matter later becomes dominant for a long period, and the component represented by lambda becomes important at late times in the standard model. Those changes can occur while the spatial curvature remains in the flat class. This is the point where the distinction we have been building becomes much more concrete. A universe can remain spatially flat while its internal balance changes dramatically with time. Flatness does not tell you whether you are living in the radiation-dominated era, the matter-dominated era, or the much later era in which dark energy has become dynamically important. The geometry has not answered that question for you. To answer it, you need the contents and the evolution. There is a compact way to see this in the language cosmologists use for density. At any epoch, the measured expansion rate defines a quantity called the critical density. In the standard Friedmann description, a spatially flat model has a total density equal to that critical value once the relevant components are included in the accounting. That does not mean every flat universe has the same absolute density. The critical density itself depends on the Hubble parameter at the epoch being considered, so a different expansion rate changes the value against which the total density is compared. Nor does flatness say how the total is divided. One flat model might assign a larger fraction to matter, and another flat model uses a different partition, while another flat model uses a different partition. Cosmologists often express those fractions with density parameters called omegas. In a flat model, their appropriately defined total is constrained to the flat value. but the individual contributions are separate quantities. Knowing the sum does not reveal every term that made the sum. Once those terms evolve at different rates, their separate identities become dynamically important. This makes the central question more precise. Two models can satisfy the same flatness condition while carrying different component densities, and the Friedmann equations then determine how those differences appear in the expansion history. In the standard Friedmann construction, the curvature index itself is part of the model and does not switch from flat to curved as matter dilutes. What changes with time are the component densities and the expansion rate. That is why a model can remain in the k=0 class while moving from a radiation-dominated era to a matter-dominated era and later to a lambda-dominated era. Imagine two bookkeeping lines that both total to the flat value. In one line, a larger share is assigned to matter and a smaller share to a vacuum-like component. In the other, the partition is changed while the sum still satisfies the flatness relation for that model at that epoch. The equality of the totals does not erase the different terms. As expansion proceeds, matter density falls while a cosmological constant remains fixed, so two ledgers that satisfied the same curvature condition can move away from one another dynamically. There is an equation that ties these ideas together, although we do not need to write it down tonight. It is one of the Friedmann equations, named after Alexander Friedmann, and it sits near the center of modern cosmology. In words, it relates the rate of cosmic expansion to the energy density of the universe, its spatial curvature, and terms associated with a cosmological constant. For a spatially flat model, the curvature term takes its flat value, but the remaining terms still contain the matter, radiation, and dark energy contributions. Because those components evolve at different rates, the expansion rate can change, while the curvature class stays the same. Ordinary language can mislead us here, because matching geometry sounds more complete than it is. When we hear that two things have the same geometry, we tend to imagine that they must behave the same way. If two roads have the same shape, perhaps the journeys along them should resemble each other. If two rooms have the same dimensions, perhaps what happens inside them should be broadly similar. Cosmology gives us more freedom than that. The geometric framework and the physical contents work together, and the contents participate in determining how the cosmic scale factor evolves. So two models can both be spatially flat, while one expands according to one history, and another expands according to a different history. The phrase shared spatial geometry has to be understood carefully here. We are talking about a shared spatial curvature class. We are not claiming that every property of their entire spacetime is identical. Once the expansion histories differ, the full four-dimensional spacetime histories differ as well. That precision matters because it keeps the question from becoming a word game. The interesting fact is not that physicists can attach the word flat to several unrelated models. The interesting fact is that spatial curvature is only one part of the cosmological description, and changing other parts can change the history without changing that curvature class. You can picture the same idea with a flat coordinate grid extending through a model universe, and then add matter and radiation to that description while allowing the cosmic clock to run. At first, let us say that the universe is young enough that radiation is still dynamically important. The expansion proceeds according to the combined influence of what is present. Allow more time to pass. Radiation loses density more quickly than matter, so the balance changes. Allow the universe to expand for far longer. Matter continues to dilute. If a cosmological constant is present, its density does not dilute in the same way, so eventually its relative importance grows. The grid can remain spatially flat throughout the story. What changes is the balance of what inhabits the cosmological model, and therefore the way the scale factor evolves. You can now see why one frozen geometric state is insufficient. Suppose we compare two widely separated epochs of one flat cosmological model. The curvature classification can be the same in both, while the radiation density, matter density, relative importance of dark energy, expansion rate, and degree of structure formation are all different. The label on the geometry can remain stable while the physical state evolves dramatically. A geometric label can remain stable while almost everything visually familiar about the cosmos develops around it. This is one reason the word universe has to carry so much more information than the word space. A A cosmological model is therefore specified by a collection of parameters rather than by one label. Some describe densities and primordial fluctuations, others govern the expansion or the properties of particular components, and together they determine whether the model reproduces the microwave sky, later structure, and distance measurements. Curvature is one constraint inside that larger fit, and this helps explain something that otherwise feels slightly puzzling about the Planck results. If the microwave background already tells us that the baseline model is consistent with spatial flatness, why do cosmologists continue measuring supernova distances, galaxy clustering, gravitational lensing, baryon acoustic oscillations, and other features of the universe? Geometry does not exhaust the model, and different observations are sensitive to different combinations of cosmological parameters, so one measurement can leave several possibilities open while another narrows the remaining combinations. And sometimes two models that look very similar through one observational probe separate clearly when viewed through another. Cosmologists call this parameter degeneracy, when different combinations of parameters can produce observational effects that are difficult to distinguish with a particular dataset. The word degeneracy sounds more dramatic than the idea needs to be. It means that one observation may not be enough to determine which combination produced what you saw. Imagine hearing only one sustained chord through a wall. Several combinations of instruments could produce something similar, but additional notes and timing information remove some of those possibilities until the underlying arrangement becomes easier to reconstruct. Cosmology often works this way. The microwave background gives an extraordinary amount of information, but cosmologists combine it with later observations because the universe has been evolving since that ancient light was released. The microwave background constrains early conditions. Galaxies trace the growth of structure. Standardized supernova observations trace the later distance expansion relation. Baryon acoustic oscillations leave another version of the early cosmic ruler, imprinted in the later distribution of matter. Each observation touches a different part of the same evolving history, and together they reveal something that no geometric label could supply on its own. Taken together, those observations begin to reconstruct a cosmic history. That biography begins long before galaxies existed, moves through changing eras of radiation and matter, and reaches the present expansion in which dark energy plays an important role in the standard model. Space is present throughout that history, but knowing its curvature does not tell you the order of the chapters. There is another way to feel the difference. Imagine two theoretical cosmologies written on separate pages, with only the curvature line visible at first. Both pages say spatially flat, so that line cannot tell you whether the models are otherwise identical. Reveal the remaining entries and the descriptions can separate immediately because the matter density radiation content and dark energy contribution can differ, so the resulting expansion histories need not match. The first line was true in both envelopes, but it never contained enough information to make the pages identical. And this is why asking whether two universes can share a curvature class turns out to be a useful question rather than a semantic puzzle. Yes, they can share a spatial curvature class, but the universe includes the rest of the page. It includes the physical contents that occupy the cosmological model and the way those contents influence its development. It includes the changing expansion rate, the formation of structure, and the history connecting one era to another, which gradually shifts the question away from geometry alone and toward the full dynamical description. We began with space as something that seemed almost complete in itself, a vast geometry within which the universe happens. Now space feels more like one coordinate in a much larger description. Important, measurable, and physically meaningful, but unable by itself to tell us which cosmic history we have been given. And once that becomes clear, a natural experiment suggests itself. Instead of speaking about all possible universes in the abstract, we can build a few very simple model universes and give them shared spatial geometry. We can make each one flat. Then we can change what fills them. In one, we can let radiation carry most of the dynamical weight. In another, matter can dominate. In another, a cosmological constant can shape the late evolution. Then we can let the clocks run and watch what happens. The geometry will not need to change class, but the histories will separate. And when they do, the distinction will no longer have to be explained as a definition. We will be able to watch it happen. Imagine three deliberately simple model universes placed side by side. They are mathematical comparisons, with no claim that three real worlds exist somewhere beyond our own. We give all three a shared spatial curvature class. Each one is spatially flat. If we could somehow construct enormous triangles inside them, their large-scale geometry would follow the same flat rules we have been discussing. Then we change only what dominates their contents. Let radiation dominate the first model, non-relativistic matter dominate the second, and a positive cosmological constant dominate the third. These are simplified universes, useful because they allow one ingredient at a time to become easy to see. Real cosmological history contains transitions between different regimes, but separating them for a moment lets us watch what the Friedmann equations are telling us. That flat curvature class can accompany very different expansion histories. They are limiting cases rather than proposals that our own universe spent its entire history with only one component present. Their value is comparative. Hold the curvature fixed, let one contribution dominate, and the effect of that contribution on the scale factor becomes much easier to see. Begin with the radiation-dominated universe. At very early times, this is the closest of our three simple models to an important part of our own cosmic history. The universe is hot, and relativistic particles and radiation carry much of the energy that matters for its expansion. Imagine placing two markers into this model, separated by a very large distance and moving only with the general cosmic expansion. As the universe grows, their separation grows. But radiation is changing at the same time. The photons become more widely distributed as the volume increases, and their wavelengths are stretched by expansion. Their energy density therefore falls especially quickly. This falling density changes how the expansion proceeds. In the simplest flat radiation-dominated Friedmann model, the scale factor grows in proportion to the square root of cosmic time. You do not need to hold the formula in your head. What matters is the shape of the history. The universe continues to expand, but the rate at which the scale factor grows changes as the radiation becomes progressively less dense. Keep that model running in the background and turn to the second one. Its space is flat too. We have not changed that. But now ordinary non-relativistic matter is the component that dominates the dynamics. Matter behaves differently from radiation because its density falls mainly through dilution. During cosmic expansion, the same collection of particles occupies an increasing volume. There is no additional loss of energy from wavelengths stretching in the same way there is for photons. That difference changes the expansion law. In the simplest spatially flat matter-dominated model, the scale factor grows as cosmic time raised to the power of 2/3. Again, the formula itself is less important than the comparison. The comparison is the important part. The radiation case grows with the square root of cosmic time, while the matter case grows with time to the 2/3 power, so two spatially flat models can follow different scale factor histories. If you could watch them from the beginning on two imaginary screens, the distinction would gradually become unmistakable. Both screens might carry the same geometric label, flat, while the distances in the two models would still develop differently as their clocks advanced. Their contents are different, so their histories are different, and the third model makes that separation even clearer while we keep the spatial curvature flat once again. This time, however, suppose the dominant contribution behaves like a positive cosmological constant. Unlike matter or radiation, the energy density associated with a cosmological constant remains constant during cosmic expansion. So while matter and radiation become increasingly dilute, this component does not fade away in the same manner. The resulting expansion has a very different character. In the idealized case dominated by positive lambda, the scale factor grows exponentially. Equal intervals of cosmic time correspond to repeated multiplication of that scale, rather than the slower power law growth of the radiation and matter examples. Now let the three model universes run side by side. Each remains spatially flat, yet one follows the radiation-dominated solution, another the matter-dominated solution, and the third the exponential behavior of cosmological constant domination. The shared curvature label has not forced the three histories to coincide. We can make that comparison stricter by choosing one reference epoch and normalizing the scale factor to the same value in all three models. The curvature label and that chosen value can then agree at the reference time, while the slopes of the three scale factor curves still differ because the density and pressure terms are different. Matching one point on the curve does not force the surrounding trajectory to match. This is the paradox in its cleanest form. If someone showed you only the spatial curvature label attached to each model, you could not identify which universe you were looking at. All three curvature labels could say the same thing, so identifying the model would require additional information about what fills it and how the component densities are divided. And once those components are specified, the Friedmann equations tell you how their gravitational effects participate in scale factor evolution. The comparison can be kept entirely inside cosmology. Write the curvature term for each model first and set it to the flat value. That line is now identical in all three descriptions. Then write the density and pressure terms beneath it. The first description is dominated by radiation, the second by non-relativistic matter, and the third by lambda. As soon as those additional terms appear, equations no longer describe the same evolution even though the curvature entry has not changed. This is a cleaner comparison than treating matter as something placed inside an unaffected background, because general relativity couples geometry and physical content. The narrower point is that matching one geometric property does not provide the entire physical state of a cosmological model. And in our three model universes, that limitation has consequences that become larger with time. Take two imaginary galaxies separated by the same initial distance in each model. Let the models evolve. Their later separations will depend on how the scale factor develops. Wait longer and the difference accumulates. Wait longer still, and what began as the same broad curvature classification can accompany histories that barely resemble one another. That is why it would be misleading to say that these models have identical space-time, because their time evolution differs, and therefore their full space-time histories differ. The sameness we are preserving is narrower and more precise. They belong to the same spatial curvature class. That qualification may seem technical, but it protects the central idea from becoming exaggerated. We do not need the universes to be identical in every spatial detail. We do not need the matter distribution to match point for point. We do not need their clocks or expansion rates to agree. The surprising fact is already present at a simpler level. Knowing the large-scale spatial curvature does not uniquely determine the cosmological evolution. There is another way to see it. Suppose you wake for a moment in one of these model universes with no memory of how you arrived. You are given an instrument capable of determining spatial curvature perfectly. Your instrument reports flat curvature, but that answer cannot tell you whether radiation, matter, or a cosmological constant is dominating the expansion. You would need additional observations, perhaps of the expansion rate, matter density, or radiation field, and each one would add another piece to the cosmological description. And eventually, as enough pieces accumulate, you are no longer describing merely spatial geometry. You are constructing a cosmological model. That transition is easy to overlook because the word universe feels so singular. There is only one observable cosmos available to us, so we naturally talk about its properties as though they belong to one indivisible package. Geometry, matter content, age, expansion, early radiation, and galaxies all arrive together in the one cosmos we observe, so ordinary language encourages us to bundle them into a single idea. The equations allow us to separate them conceptually. They allow us to ask what would happen if one ingredient changed while another property remained fixed. And when we do that, the distinction becomes much clearer. Spatial curvature describes one aspect of the framework. The cosmological model contains a fuller set of physical information. Our three imaginary universes demonstrate that without requiring anything exotic, no extra dimensions are needed, no hidden cosmos has to be discovered, no speculative theory has to rescue the idea. Ordinary Friedmann cosmology already gives us enough freedom for a radiation-dominated flat model, a matter-dominated flat model, and a lambda-dominated flat model to follow different expansion histories without changing the shared curvature class. And this gives us the first major answer to the question we began with. Two universes can have the same kind of large-scale geometry without having the same cosmic history. In fact, our simple experiment gave us three. But there is something we have not yet examined carefully. We have watched the scale factor behave differently, and we have said that the ingredients are responsible for that difference. We have not yet followed the mechanism closely enough to see why radiation, matter, and lambda pull the history into such different shapes. That is the next layer of the question, because once we understand how the contents alter the expansion, the universe stops looking like a static collection of things inside space and begins to look like what cosmology actually describes: an evolving physical system whose past and future cannot be read from geometry alone. The expansion depends on both how much energy is present and how each component carries pressure while the universe grows. That is the part the three model universes were hiding from us. We gave one universe radiation, another matter, and another a cosmological constant, and their scale factors followed different histories, even though all three were spatially flat. We can now look more closely at why that happens, because the answer sits inside the relationship between density, pressure, and expansion. Begin with the expansion rate itself. Cosmologists usually describe it with a quantity called the Hubble parameter. It tells us at a particular cosmic time how rapidly the cosmic scale changes relative to its current size. The Hubble parameter today has a particular value, but it is not a universal clock rate that has remained fixed throughout cosmic history. In general, it changes as the universe evolves. The Friedmann equation connects that expansion rate to the contents of the cosmological model, along with spatial curvature and, depending on how the equation is written, the cosmological constant. For the flat models we have been imagining, the curvature contribution takes its flat value. That removes one piece of the equation, but it does not decide the expansion history because the matter, radiation, and vacuum-like density terms still remain. And those densities do not all change in the same way. Suppose we begin with matter. For ordinary non-relativistic matter, the important thing is that the number of particles inside a comoving region can remain the same while the volume associated with that region grows. If every large cosmic distance is multiplied by the scale factor, then a three-dimensional volume grows with the cube of that scale factor, so the matter becomes more dilute. A region that once contained a certain amount of mass still contains that mass, but the same mass is spread through a larger volume. As a result, the average matter density falls during cosmic expansion. Radiation also becomes diluted because photons are spread through an increasing volume, but radiation has an additional effect. Expansion stretches the wavelength of each photon. A longer wavelength means lower photon energy, so the radiation density falls because the photons are becoming more widely separated and because the energy carried by each photon is decreasing. This is why radiation thins out faster than matter. If we trace the history backward, the same relationship works in reverse. Radiation density rises more rapidly than matter density when we trace the expansion backward toward a smaller cosmic scale, which is why radiation was much more important in the early universe than it is now. This is not a separate rule added merely to make the cosmological timeline work. It follows from the way radiation behaves in an expanding geometry. And that gives us the first part of the mechanism. The universe changes its dominant ingredient because different forms of energy dilute at different rates. But density is only half of the story. Pressure also matters. In ordinary life, it sounds local, like gas pressing on a cylinder, but in general relativity, pressure contributes to the gravitational behavior of a cosmological fluid. Cold matter has negligible pressure compared with its energy density. Radiation has positive pressure, while lambda is associated with negative pressure together with constant energy density. And this difference in pressure helps determine whether the cosmic expansion slows or accelerates. There is a second Friedmann equation, often called the acceleration equation, that makes this especially clear. It relates the scale factor's acceleration to the energy density and pressure of what fills the universe. Matter and radiation both contribute in a way that tends to slow the expansion. They do not necessarily cause an expanding universe to reverse and collapse. Their gravitational contribution makes the expansion decelerate compared with what it would otherwise do. the cosmological constant behaves differently. Its effective negative pressure allows it to drive accelerated expansion. This is why our third model universe separated so dramatically from the first two. The difference came from the physical density and pressure assigned to the dominant component. We had changed the relationship between energy density, pressure, and scale factor evolution. Now return to our three imaginary screens. The first screen contains the radiation-dominated universe. Radiation has positive pressure, and its density falls rapidly as expansion stretches both the distribution of photons and their wavelengths. The universe expands, but the expansion decelerates. The second screen contains the matter-dominated universe. Matter has very little pressure in the cosmological approximation, and its density falls more slowly than radiation density. This universe also expands with a decelerating history in the simple model, but its scale factor follows a different time dependence because the dominant component behaves differently. The third screen contains the universe dominated by positive lambda. Here the cosmological constant keeps a constant energy density during expansion, and its negative pressure changes the acceleration equation in the opposite direction, producing accelerated expansion, even though the spatial curvature class remains flat. At that point, the phrase shared spatial geometry clearly tells us less than the full cosmological history. If you stood inside one of those models and measured only the spatial curvature, you could receive the same answer in each case. But if you watch the distances between widely separated comoving galaxies evolve over a long enough interval, the histories would tell you which kind of universe you were in. Geometry provides one part of the measurement, dynamics provides another, and the cosmological identity requires both kinds of information. There is a useful way to organize all of these different cosmic ingredients, and it comes from comparing pressure with energy density. Cosmologists often use a quantity called the equation of state parameter, usually represented by the letter W. It is essentially a compact way of saying how much pressure a component has relative to its energy density. For non-relativistic matter, W is approximately 0, for radiation it is 1/3, and for a cosmological constant it is -1. These are three concrete cases rather than a rhetorical list, and each value corresponds to a different way the component density changes during expansion. Those numbers may look small and harmless, but they encode very different cosmic behavior. Once you know a component's equation of state, you can determine how its density responds to expansion. Matter with W close to 0 dilutes with volume. Radiation with positive pressure loses density faster. A cosmological constant with W equal to -1 keeps constant density as space expands. So the equation of state acts like a bridge between what something is physically and how it participates in cosmic history. This is why the total amount of energy at one selected moment is not enough by itself. If that total is divided differently among matter, radiation, and a vacuum-like component, the later evolution can separate because the components scale differently. Radiation loses density fastest, matter more slowly, while a true cosmological constant keeps constant density. So an apparent similarity at one epoch need not survive as time passes. The future reveals the difference that a single snapshot concealed. This gives our instantaneous state thought experiment another layer. Even if our frozen epoch experiment gave us both the curvature and the total energy density at that moment, we would still need to know how the total is divided among components, because different partitions can lead to different later behavior. If one model contains mostly matter and another contains a large vacuum energy contribution, their future expansion can differ even if a carefully chosen snapshot makes some of their present quantities look similar. A state at one moment does not become a complete cosmic history until the physical rules connecting that state to earlier and later times are specified. At this point, cosmology needs a dynamical description of a moving system. A photograph can show the position of a pendulum, but it cannot tell you where the pendulum will be later unless you know something about its motion and the forces acting on it. In the same way, spatial geometry gives us part of the cosmic state, but the expansion history emerges from the contents and their physical behavior. Our own universe passed through changing regimes because these components did not remain equally important. Radiation mattered enormously in the early cosmos, but its density declined rapidly. Matter later became dominant, giving gravity long periods in which to amplify small early density variations into larger structures. Much later, the component described by the cosmological constant in the Standard Model became important enough for the large-scale expansion to enter an accelerating phase. The universe did not need to change from flat space into some completely different spatial curvature class for those transitions to happen. The balance of the contents changed. That distinction is one of the cleanest answers to the question we began with. The history of a universe is not written solely in the curvature of its space. It is written in how the densities and pressures of its contents evolve with cosmic expansion. And this gives us something we can actually test. If the late universe really entered an era of accelerated expansion, there should be observations that reveal that change through the distance history of the cosmos. We should not have to accept it because an equation permits it. We should be able to look outward and find evidence that the expansion has behaved differently from what a simple matter-dominated universe would predict. Near the end of the 20th century, astronomers tried to make exactly that kind of measurement using distant exploding stars. They were expecting the expansion to show the slowing influence of matter. The light that returned carried a different message. For a long time, one of the simplest expectations in cosmology was that an expanding universe filled with matter should gradually slow down. The reasoning was straightforward because matter gravitates, so in a universe where matter provides the dominant contribution, its attraction should make an already expanding cosmos decelerate. The universe might continue growing forever, or under some models it might eventually turn around. But either way, if matter were doing most of the dynamical work, the expansion in the past should leave a recognizable pattern in the way distance accumulates with look-back time, that gave astronomers something they could try to measure. They needed objects bright enough to be seen across enormous distances and predictable enough that their apparent brightness could tell us something about how far away they were. One of the best tools available was a particular class of stellar explosion called a type Ia supernova. These explosions vary from one event to another, and their light curves can still be calibrated well enough to estimate their intrinsic luminosities. Once astronomers have an estimate of how luminous such an explosion really was, they can compare that with how faint it appears from Earth and infer a luminosity distance. The calibration matters because the cosmological conclusion depends on distinguishing a genuinely greater distance from a supernova that merely happened to be intrinsically dimmer or more heavily obscured. The original high redshift analyses therefore compare different light curve fitting methods and examine possible systematic effects such as extinction, sample selection, and evolution. The acceleration result was not produced by treating every type Ia explosion as literally identical. The light also carries a redshift, so each distant supernova gives two kinds of information that can be compared. How far away does it appear to be? And how much has the universe expanded since its light began traveling toward us? By gathering enough of these events at different redshifts, astronomers could begin reconstructing the recent expansion history of the universe rather than measuring only the present expansion rate. And in the late 1990s, the result did not fit the simplest expectation. The distant supernovae appeared fainter than they would have in a universe whose expansion had been slowing in the expected way under the influence of matter alone. Fainter in this carefully calibrated context meant farther away. The light had crossed more expansion than the simple decelerating picture predicted. The result favored a late-time expansion that was accelerating rather than the simple matter-only deceleration the teams had expected. In the 1998 High-Z Supernova Search Team paper led by Adam Rias, the analysis combined 16 high redshift type Ia supernovae with 34 nearby events. On average, the high redshift supernovae lay about 10 to 15% farther away than expected in a low-density universe without a cosmological constant. Different light curve fitting methods and checks for systematic effects still favored a positive cosmological constant and present acceleration. Those numbers matter because they turn the later expansion from a verbal possibility into a measured distance discrepancy that a matter-only model had to explain and could not. The paper also treated extinction, selection effects, possible evolution, local flows, lensing, and sample contamination as sources of systematic uncertainty. None of the examined effects reconciled the data with a non-accelerating zero lambda interpretation in that analysis, which is why the result survived as an observational turning point rather than as one anomalous set of faint explosions. If these long, quiet questions are useful company at night, you can subscribe and leave the next one waiting for another evening. There is something useful about staying with the observation before we rush toward its interpretation. Imagine a single distant supernova. Its explosion happened billions of years ago. For a brief period, it became enormously luminous and then it faded. The photons that left during that explosion traveled through an expanding universe for a significant fraction of cosmic history before reaching a telescope on Earth. During their journey, the universe continued changing. So when astronomers measure that supernova, they are not looking at the expansion as it is tonight. They are looking backward through scale factor history. Now collect calibrated supernovae across a range of redshifts. Some are relatively nearby, so their light began traveling more recently. Others are much farther away, so their light left at an earlier cosmic epoch. Arrange those measurements carefully, and the collection becomes something like a record of how distance has accumulated through cosmic time. This is why the supernova result mattered so much to the question we have been following. Spatial curvature and expansion history are connected within cosmological models, but they are not the same observable. A flat universe is not automatically a matter-dominated universe. A flat universe is not automatically a universe expanding at one particular rate. And a flat universe is certainly not required to follow one unique future. The supernova observations made that distinction difficult to ignore. Under a spatially flat model, the data favored a substantial positive contribution from the cosmological constant rather than a universe containing only matter. The geometric label could therefore remain flat while the history attached to that label changed. Instead of a late universe in which matter continued to dominate the expansion, the observations pointed toward a universe in which something with the behavior of dark energy had become dynamically important. That change affects the scale factor. It affects distances. It affects what the universe may look like in the far future. Yet it does not require the spatial geometry to leave the flat class used in the baseline model. This is the observational version of the experiment we performed with our three imaginary universes. There, we changed the contents and watched the mathematical history separate. Here, astronomers looked at actual light from distant explosions and asked which kind of history best matches the distances we observe. The equations had told us that several flat histories were possible. The supernovae helped tell us which broad kind of late-time history our own observable universe was following. That distinction matters because physics can allow several mathematically consistent possibilities, while observations remove the ones that do not match the universe we actually see. A flat matter-dominated model can be written down. A flat model containing a cosmological constant can also be written down. Geometry by itself does not choose between them, so another observation has to carry the next piece of information, and distant supernovae provided one way to do that. Their answer was not delivered as a voice or a message. It was hidden in the amount of light reaching our telescopes after billions of years of travel. The high redshift supernova was systematically farther away than the matter-only expectation, and repeated measurements turned that distance difference into evidence for accelerated expansion. The procedure itself remained patient. Astronomers calibrated the light curve, measured the redshift and apparent brightness, inferred the distance, and compared the distance-redshift relation with competing cosmological histories. The value of this method comes from its dependence on history rather than on a single present-day number. A nearby supernova samples a shorter stretch of expansion, while a more distant one samples a longer stretch. Placing many calibrated events at different redshifts lets the curve of distance against redshift reveal whether the expansion has behaved like a simple decelerating matter model or requires an accelerating component at late times. The comparison is therefore geometric and dynamical at once. Redshift records how much the cosmic scale changed along the light's journey, while luminosity distance records how faint the standardized event appears after traveling through that evolving geometry. A model has to reproduce both sides of that relation across the sample, not merely fit one supernova in isolation. This is a useful place to remember the microwave background, because it gives us an extraordinarily early anchor, while the supernovae give us a much later one, leaving an immense span of cosmic history between the two records. The ancient radiation constrains conditions in the young cosmos. The supernovae tell us how expansion behaved billions of years later. When those measurements are combined with other cosmological observations, the model becomes increasingly constrained. The need to combine them reveals why no single label carries the whole description, because flatness does not determine the matter density or replace the later expansion measurements. Matter density is not doing the work of the expansion history. The microwave data and the supernova data do not perform the same inferential job. Each measurement answers a different part of the larger question. This is why the phrase "the universe is flat" can be true and still leave a surprising amount unsaid. It tells us about large-scale spatial curvature. It does not tell us by itself whether the expansion is currently speeding up or slowing down. It does not tell us which component dominates at a particular era. It does not tell us how long matter remained dynamically dominant. It does not tell us the exact path the scale factor followed between the young universe and today. And it does not tell us what that path will become in the distant future, unless we also know how the relevant cosmic components behave. The supernova measurements, therefore, give us something more interesting than the discovery of acceleration alone. For our purposes tonight, they show how two questions that sound almost identical can separate once you try to measure them. What is spatial geometry? And how has the universe expanded? The answer to the first does not contain the complete answer to the second. You can imagine knowing one with extraordinary precision, while still needing observations to determine the other. That is enough to replace a static picture of cosmology with a dynamical one. Curvature can be measured at an epoch, but a universe has to be described through the way its state changes with time. Now imagine an impossible survey that records every large-scale position and distance available inside the observable region at one chosen epoch, together with the intrinsic spatial curvature. No spatial relation in that census is missing. The result would be far more complete than anything a real telescope could produce. Yet the supernova story tells us why it still would not identify a unique history. The census does not by itself record the expansion rate, its acceleration or deceleration, or how the component densities and pressures are divided. Those extra quantities are the information that connects the selected epoch to the epochs before and after it. So the original question can now be sharpened. The model universes showed that shared flat curvature can coexist with different histories, and the supernovae showed that expansion history must be measured rather than inferred from curvature alone. If every spatial relation at one epoch were known perfectly, what dynamical information would still be missing? A surprising amount would still be missing, because a complete spatial census of one epoch does not automatically tell you how that state is changing. Our impossible observer may know every large-scale distance, every galaxy position, and the intrinsic curvature at that epoch, so nothing spatial in the census has been overlooked, but the cosmological state is still incomplete until its dynamical information is added. The easiest way to see why is to replace the universe for a moment with something much smaller. Imagine a pendulum suspended in a dark room. You take a photograph at exactly the moment when the pendulum is slightly to the left of center. The photograph can tell you where the pendulum is. It cannot tell you whether the pendulum is moving farther left, moving back toward the right, or has somehow been held motionless at that position. Those three situations can share the same photograph. Their futures are different because position is not the only information that matters. You also need motion. Cosmology has a much larger version of that problem. A spatial census describes relationships at an epoch, including how far things are from one another and what intrinsic geometry those distances obey. But the universe is not a collection of distances that have stopped changing. Those distances participate in an evolving space-time. So beside the question of intrinsic geometry sits a second question about how the large-scale state is changing with time. In the simplified homogeneous cosmological models we have been using, that change is captured largely by the scale factor and its rate of evolution. Two models could therefore be arranged to have the same scale factor at one chosen instant. At that instant, if we normalize them in the same way, their broad spatial geometry could look identical. One model might be expanding more rapidly, another more slowly, and a different hypothetical solution could even be contracting, although all of them can be compared at an instant when selected spatial quantities agree. Those instantaneous measurements alone would not reveal which history you had entered. This is why a scale factor at one moment is not the same thing as an expansion history. You need the expansion rate as well. And even that is not quite enough, unless you also know what is causing the change. Return to the three model universes from earlier. Suppose we choose one special moment in each model and normalize them so that the scale factor has the same value while the spatial curvature is flat in all three. If we inspect only those quantities, the descriptions can look deceptively similar, but adding a measurement of the expansion rate begins to separate some of the possibilities. But imagine that two different models have been chosen so that even their expansion rates happen to agree at that single instant. Even matching the instantaneous expansion rate would not necessarily remove the ambiguity, because the component contents could still differ. One could contain more matter and a different contribution from dark energy. Another could contain a different mixture that produces the same instantaneous expansion rate at the moment you happen to measure. As time passes, those different ingredients can cause their histories to diverge. The problem, therefore, requires more than a single state variable, because a position does not specify a history, and even a first rate of change may be insufficient when different physical contents produce different accelerations. To predict what comes next, you need the physical rules and the physical state that those rules act upon. Cosmology needs the same kind of completeness. For a simple Friedmann model, the necessary information includes the densities of the important components, the way those components behave during expansion, the expansion rate, the curvature, and the equations connecting those quantities from one moment to another. Once enough of that state is supplied, the evolution is no longer arbitrary. This is much more information than the single line that labels the spatial curvature as flat. In the highly symmetric models used here, this additional information can be compressed into a small set of functions and parameters. That economy is helpful because it shows exactly where the freedom lives. Curvature determines one relation. The Hubble parameter gives the first rate of change, and the pressure content enters the acceleration. If two models agree only on curvature, they have not yet agreed on enough information to force the same future. There is a deeper version of the same idea in general relativity. The intrinsic geometry specified at a single epoch does not, by itself, contain all of the information about the surrounding space-time. One also needs information about how the spatial state is changing within the four-dimensional geometry. Physicists have a precise mathematical language for this, but the intuition is simple enough to keep without the formalism. A shape can tell you what a moment looks like. It does not necessarily tell you how the next moment will differ. Think of a calm ocean photographed from directly above. The surface could appear almost perfectly smooth. From the photograph alone, you would not know whether the water was truly still, whether a long swell was passing beneath the camera, or whether two large currents were moving in opposite directions without producing much visible texture at that instant. The surface shape matters, but motion carries additional information, and our imagined cosmic census has the same limitation. It could tell us the intrinsic geometry of space at the chosen moment. If we have also mapped the matter distribution, it could tell us where the galaxies and clusters are. But if we have removed all information about their motion and all information about the changing cosmic scale, then we have removed part of the universe's dynamical state. And without that dynamical state, the future cannot be read from that state alone. This is one reason astronomy depends so heavily on light carrying more than an image. A spectrum can reveal redshift, a changing signal can reveal motion, and a sequence of observations can reveal evolution, so astronomical light carries more than a static image. Different kinds of evidence allow us to reconstruct a story, that a static photograph cannot contain. This ancient radiation is useful, partly because it gives us a view from an earlier chapter. We do not possess only the universe as it is now. We receive ancient light from different distances and therefore from different times. The farther outward we look, the farther backward along our past light cone we are seeing. The night sky is not a single instantaneous photograph of the cosmos. It is a mixture of times. The moon is seen as it was a little more than a second ago. The sun is seen as it was several minutes ago. Nearby stars are seen years in the past. Distant galaxies appear as they were millions or billions of years earlier. Cosmology turns that unavoidable delay into information. We cannot freeze the entire universe and inspect one universal present from outside it. Instead, we receive light that has traveled through different stretches of cosmic history. That makes observation harder in one sense, but richer in another. The universe shows us change because distance and look-back time are tied together by the finite speed of light. Still, even this enormous archive of ancient light does not remove every ambiguity automatically. Observations have to be interpreted through physical models. If two models make similar predictions for one set of measurements, another kind of observation may be needed to separate them. That was the degeneracy we encountered earlier. This is a normal feature of inference in cosmology. Several parameters can leave overlapping effects in one observation, so another observation may be needed to separate them. Sometimes several different physical ingredients leave overlapping fingerprints. The solution is not to stare harder at the same fingerprint. It is to look for another one. This is why cosmologists combine measurements made from very different parts of the universe's history. The microwave background gives information from the young cosmos. Large-scale structure tells us how matter later gathered. Supernovae trace the relationship between redshift and luminosity distance in the later universe. Other distance measurements add still more constraints. The useful constraints emerge where independent observations intersect. One measurement can leave a broad corridor of possibilities, while a second and third cut across it until the allowed cosmological histories become much more specific. There is something almost philosophical hiding inside this procedure, though it does not require us to leave physics. Knowing where things are at one epoch does not completely characterize a cosmological model. The phrase "where things are" sounds spatial. The phrase "what the universe is" turns out to require change. It requires relationships across time. That distinction becomes especially clear if we imagine destroying every record of the past. Suppose the complete present-day census survives while the ancient records are erased. The ancient radiation is gone, distant galaxies no longer show earlier stages of cosmic history, and no supernova light remains from events billions of years ago. You could still know every present distance, the curvature, and even the matter distribution, while losing our reveals how the universe reached that state. The present contains clues to its past, certainly. The laws of physics place strong constraints on what could have happened. But the present spatial census would still not contain the full expansion history. The missing information concerns dynamics. Galaxies formed, stars were born and died, radiation cooled as its wavelengths stretched, matter became increasingly structured under gravity, and the relative importance of the cosmic components changed, while the expansion rate changed with them. A single epoch can preserve consequences of those processes without telling us their full time dependence. A complete spatial census of one epoch can contain results of the preceding history without encoding that entire history in the curvature alone. And now the question has changed slightly. At first, asking whether two universes could share flat curvature sounded like a puzzle about definitions. Then the three flat model universes showed that it was really a question about dynamics. Now we can see something even more precise. Two cosmological descriptions can share a spatial curvature class, because curvature does not carry all of the information required to specify an evolving universe. A universe needs something like a state and a law of evolution. The spatial geometry, the physical contents, and the relevant rates of change all belong to the state we need to specify, while the physical laws connect that state to earlier and later ones. Remove enough of those pieces and the description stops being a complete cosmological history. This also changes the meaning of our imagined complete census. Such a census would be extraordinarily useful because complete knowledge of cosmic curvature would remove whole classes of cosmological possibilities. It would still be incomplete if it lacked the dynamical quantities needed to connect that epoch to earlier and later ones. There is no contradiction in having exact geometric knowledge and incomplete dynamical knowledge. The shape of a wave at one moment, for example, does not determine its later motion unless the state and governing dynamics are also specified, and spatial curvature has the same limited role in a cosmological model. And that brings us toward a darker, quieter question. Because once we admit that the present geometry cannot specify the whole cosmic history, the future becomes dependent on something else. It depends on what the universe contains and on how those contents continue to behave. Matter and radiation are described by well-tested physical theories, while the component associated with the late accelerated expansion remains less deeply understood. We call it dark energy, and cosmological models can measure its effective role, but the name does not identify its underlying physical nature. And if the future expansion depends on that component, then even a universe whose geometry we understand very well can still keep part of its ending hidden. If the future of the universe depends on what fills it, then knowing spatial geometry can never be quite the same as knowing how the story ends. That distinction is easy to miss because geometry once seemed closely tied to cosmic fate. In simpler cosmological pictures, it was tempting to imagine a neat correspondence. A positively curved universe might eventually stop expanding and collapse. A flat universe might expand forever at an ever slower rate. A negatively curved universe might also expand forever. The geometry appeared to carry the ending within it. But that simple connection depends on what kind of contents you assume. Once a component such as dark energy is included, spatial curvature alone no longer tells you whether expansion will slow, accelerate, or behave in some more complicated way. A model with flat spatial curvature can accelerate. A curved universe can also behave in ways that cannot be inferred from the sign of its curvature alone. The possible ending therefore depends on the dynamics, which in turn depend on the contents and their physical behavior. Our own observable universe gives us a particularly interesting version of this problem, because its late expansion is accelerating, while the baseline lambda CDM model describes its large-scale geometry as very close to flat. So the word flat cannot possibly mean that the universe is drifting towards some simple, neutral future in which expansion merely coasts along. The geometry is flat while the expansion is accelerating. Those statements describe different properties. To understand what might happen next, cosmologists have to ask what is responsible for the acceleration and how that component behaves as the universe continues to expand. The name dark energy is useful, but it should not be mistaken for a complete explanation. It is a name for whatever is producing the observed late-time behavior in the cosmological model. In the standard lambda CDM picture, the simplest description is a cosmological constant. That is the lambda we encountered earlier. If lambda really is constant in exactly the way the model assumes, then its energy density does not become diluted as matter and radiation do. Matter continues spreading through larger volumes and radiation loses density even more rapidly, while the contribution associated with lambda remains, so its relative importance grows. The farther the universe expands, the less important matter becomes to the overall expansion, compared with that constant contribution. Under that assumption, accelerated expansion continues, the scale factor keeps growing, and regions that are not gravitationally bound become more widely separated. And the large-scale universe becomes progressively more dilute in matter, even though the dark energy density associated with the cosmological constant remains unchanged. This is already enough to create a future that could not have been read from spatial flatness. Return to the imagined complete census. At the epoch when the census was made, suppose the spatial curvature was flat. Let the model run for billions of years and then much longer. If a cosmological constant continues to dominate, the spatial curvature classification can remain flat while the observable large-scale environment changes enormously. Galaxies outside gravitationally bound groups continue to recede. Light from sufficiently distant regions takes longer and longer to reach any one observer. Over very long times, more of the universe becomes causally inaccessible to that observer, because accelerated expansion prevents newly emitted light from some sufficiently distant regions from ever arriving. This statement refers to a cosmological event horizon in the lambda-dominated extrapolation, not to a galaxy crossing the Hubble radius at one moment. The Hubble radius and the event horizon are different concepts, and only the latter answers the question of whether a signal emitted sufficiently late can ever reach the observer. Keeping that distinction clear prevents a useful far-future picture from turning into a misleading claim that every receding object vanishes the instant its recession rate exceeds the speed of light. Spatial curvature did not announce this future by itself. It follows from the behavior assigned to the dominant energy component, which becomes especially consequential over very long timescales. Spatial curvature can remain flat, while the amount of universe that any future observer can receive information from becomes increasingly restricted. The spatial structure is not suddenly collapsing or tearing in the ordinary sense. Instead, the expansion history changes what can communicate with what. This is one reason the far future of cosmology feels very different from the far future of a planet or a star. A star has a local environment. A planet has an orbit. Their futures can be complicated without the large-scale causal relationships around them changing very much. In an accelerating cosmological model, those causal relationships do change, because sufficiently distant regions can eventually lose the ability to exchange new signals. And yet even this is not the most important uncertainty. The more basic question is whether the cosmological constant is the complete description of dark energy. The cosmological constant remains the reference assumption inside lambda CDM, while the physical nature and possible evolution of dark energy remain unresolved. That means we have to separate two statements very carefully. We can measure the expansion history well enough to know that the late universe has undergone accelerated expansion. But knowing that acceleration occurs is not the same as knowing the ultimate microscopic nature of the component responsible for it. Those are different levels of knowledge. And once again, one level can be extremely precise while the next remains open. This creates several possible ways of thinking about the far future, although only one should be treated as the baseline picture. If dark energy is exactly a cosmological constant, then the simplest expectation is continued accelerated expansion. Matter becomes increasingly dilute on the largest scales. Radiation becomes even less important. Bound systems can remain bound locally, while the distances between widely separated unbound regions continue to grow. The universe becomes colder and emptier on very large scales. This does not require space to reach an edge or flatness to fail. It follows from continued scale factor growth, while matter becomes increasingly dilute on large scales. That is the conventional picture inside lambda CDM. But physicists can also study models in which the component driving acceleration behaves differently. Its pressure could have a different relationship to its energy density. Its effective equation of state could vary with time. A component that looks very similar to a cosmological constant over the span we have measured could, in principle, behave differently over vastly longer periods. These alternatives are model possibilities, not discoveries. A convenient way to describe those alternatives is again the equation of state parameter W. A true cosmological constant has W equal to -1 and a constant energy density, a component with another value, or with a value that changes with evolves and therefore change the far future expansion. Some theoretical choices approach a cosmological constant closely enough to resemble it, falling only over much longer intervals, while separating only over much longer intervals. That is why statements about the distant future are always conditional on the assumed dark energy behavior. Continued accelerated expansion is the baseline consequence of positive lambda, not a prediction produced by flatness alone. If future observations eventually require a different equation of state, the expected fate would have to be recalculated even if the spatial curvature measurement remained essentially unchanged. That distinction matters. The fact that equations allow a future does not mean nature has chosen it. Cosmology constantly works inside that boundary. It helps to keep three levels separate, namely behavior required by present observations, behavior still allowed by them, and mathematical possibilities that extend beyond the range we can currently test. For our question tonight, though, the existence of several mathematically possible futures is enough to make one point especially clear. Flat spatial curvature does not impose one predetermined ending on a cosmological model. The future depends on the dynamics set by the universe's contents and by the way those contents behave. This changes the emotional character of the word universe. Earlier, the two words could sound as though they differed mainly in scale, but the cosmological distinction is now clearer. Geometry describes spatial relations at an epoch, while the model also has to connect the radiation-dominated early universe, the long matter-dominated period, the formation of stars and galaxies, the later acceleration, and whatever evolution follows. In cosmology, the universe is described as an evolving solution rather than only as the collection of things present at one epoch, which makes our present observational moment feel unusually narrow. We live during an era in which galaxies are still plentiful across the observable sky. The ancient radiation is still measurable, large-scale structure can still be mapped, and distant supernovae can still be used to trace expansion. Several different chapters of cosmic history remain visible to us at once, because their light is only now arriving. A far future observer in a continually accelerating universe could inhabit a very different observational situation. Much of the evidence that is accessible to us may no longer be accessible in the same way. The universe would still have a history, but the observable clues available from one location could become poorer. That possibility gives cosmology an unusual relationship with time. We usually expect scientific progress to improve with better instruments, longer records, and more precise measurements, but some cosmological evidence also depends on the epoch in which an observer happens to live. The sky itself changes with cosmic time. The radiation background continues to cool and redshift, distant structures evolve, and the expansion alters which signals can eventually reach a given observer. Knowledge does not exist independently of cosmic history. The universe determines which evidence is available at a given time. There is no need to make that frightening. It follows from living inside the object being studied. We do not stand outside the universe while it changes. Our laboratories, rulers, and clocks are all part of the same evolving system, and every photon used as evidence has traveled through the history we are trying to reconstruct. This is why a spatial census, however precise, cannot replace an expansion history. It can record where galaxies lie at the chosen epoch, while cosmology also asks how that arrangement emerged, how the scale factor was changing, and which future signals remain capable of reaching an observer if accelerated expansion continues. So even a complete flat geometry census would not by itself answer whether expansion continues forever in a particular model. We would still need the matter and radiation content, the nature of the component driving the late acceleration, and the way its equation of state behaves during expansion before the equations could carry the model forward. And even then, our confidence would extend only as far as the physical assumptions and observations supporting the model. The conditional wording matters, because a scientific prediction inherits the assumptions of the model used to make it. Lambda CDM gives a remarkably successful baseline description of the universe we observe. Within that model, continued accelerated expansion follows naturally from positive lambda. But science leaves the door open where the evidence leaves it open. The word lambda is part of a model. The deeper nature of dark energy remains a question. And because that question concerns the component dominating the late-time expansion, it is also a question about the distant future. By this point, the original question has become more precise. Shared flat curvature can coexist with different mixtures of cosmic components, and because those components carry different densities and pressures, the corresponding models can follow different expansion histories and different futures. The remaining task is to state exactly what flatness needed and what a cosmological model is needed before a cosmological model is identified. There is a compact mathematical way to finish the argument, and it makes the distinction precise without relying on metaphor. In a homogeneous and isotropic Friedmann model, spatial curvature is represented by a curvature term usually written with the symbol k. When k is 0, the spatial geometry belongs to the flat class. The Friedmann key equation then relates the expansion rate to the total energy density of the model. At any chosen epoch, physicists can define a density from the Hubble parameter, and in the flat case, the total density matches that critical value once all relevant components are included in the accounting. That statement is stronger than saying only that triangles behave as they do in Euclidean geometry, but it still does not tell us how the total density is divided. Matter can provide one fraction, radiation another, and dark energy another. Different mixtures can satisfy the flatness condition, because flatness constrains the total relation between density and expansion, rather than assigning a unique value to every component separately. There is another subtle point hidden inside the phrase critical density. It is not one fixed amount that every flat universe must contain. The critical density depends on the expansion rate at the epoch being considered. Two flat cosmological models can therefore have different Hubble parameters and different absolute densities, while both satisfy the flat condition appropriate to their own histories. Even if two models are arranged to share the same expansion rate and total density at one selected moment, different partitions among matter, radiation, and dark energy can still produce different accelerations, because pressure enters the dynamics as well. The second Friedmann equation makes that point especially clear. It is sensitive to energy density and pressure, so two models can agree on quantities that describe one instant and still disagree about the way the next interval develops if their pressure content differs. Radiation carries positive pressure. Cold matter contributes very little pressure in the cosmological approximation, while lambda contributes negative pressure. The distinction appears in the curvature of the scale factor curve through time. In other words, the first equation constrains the instantaneous expansion rate, while the acceleration equation constrains how that rate changes. Together, they show why the same curvature condition can coexist with more than one dynamical path. This is why a complete cosmological state cannot be reduced to the appearance of one spatial state. In the symmetric Friedmann models, the Hubble parameter gives the first rate of change, while the acceleration tells us how that rate evolves. Curvature, expansion rate, component densities, and equations of state work together. Leave one family of information out, and more than one history can remain compatible with what was measured. Another way to see the same point is to ask what would happen if two models were tuned to agree at one chosen epoch. They could share k equal to 0, the same normalized scale factor, and even the same instantaneous Hubble parameter. If the matter and dark energy mixtures differ, however, their accelerations need not agree, and the histories can separate immediately on either side of that epoch. Their different accelerations carry information that the shared geometry does not. This is the cleanest version of the mechanism we have been circling around all night. Flatness places a constraint on a cosmological model, but it does not serve as an identity card for that model. To identify the model more fully, we need to know the densities of its components, the equations of state that describe how those components behave, the initial conditions that seed later structure, and enough of the expansion combination actually matches the universe we observe. Those pieces are related by the same equations, so can they be recovered from the curvature label without limit, but neither can they be recovered from the curvature label alone. The three simplified universes make this visible. In the radiation-dominated case, positive radiation pressure and rapidly declining radiation density produce one scale factor history. In the matter-dominated case, negligible pressure and slower dilution produce another. With positive lambda dominating, constant vacuum density and negative pressure produce accelerated exponential expansion. All three examples can be written with k equal to 0, even though the functions describing their scale factors are different. So the answer is yes, with one important qualification. Two cosmological models can share a spatial curvature class and still differ in every physical feature that matters for their cosmological evolution. They can contain different mixtures of energy, expand at different rates, form structure differently, and approach different late-time behavior. That answer is more limited than saying two universes have identical space in every possible sense. Their full spacetimes are not identical once their expansion histories differ, and their matter distributions do not have to match. The shared feature is specifically the intrinsic curvature class of spatial slices in the models we are comparing. The distinction also explains why observations arrive in families rather than as one decisive observation. Planck measured the microwave sky with enough precision to constrain the angular acoustic scale and fit the standard 6-parameter flat lambda CDM model, but those parameters still include separate information about ordinary matter, dark matter, primordial fluctuations, and other quantities. Supernova measurements then probe the later distance redshift relation, and large-scale structure measurements add information about how matter grew and how characteristic early universe scales appear at later times. A successful cosmological description has to make those different records agree. That agreement is more informative than any single label. If a proposed flat model fits the microwave acoustic scale but requires a late expansion incompatible with supernova distances, the model fails as a complete history. If a different matter density improves one feature but ruins the peak structure or later clustering, that trade does not produce a better universe merely because the curvature stayed flat. The model has to survive the intersections among observations. The early microwave pattern cannot demand one expansion history, while the later supernova distances demand an incompatible one. Matter densities inferred from one probe cannot be chosen freely if they spoil another. The model becomes credible because one connected set of physical assumptions survives several kinds of measurement across widely separated epochs. This is also why the phrase "the universe is flat" should be heard with care. It is convenient shorthand for a statement about large-scale spatial curvature within a cosmological model, not a complete summary of the universe. The same shorthand can sit above more than one theoretical history, just as the symbol k=0 can appear in more than one Friedmann solution. None of this makes curvature unimportant. Curvature changes distance relations, changes how standard rulers project onto the sky, and occupies a fundamental place in the cosmological equations. The correction is to stop asking curvature to answer questions that belong to other parameters. Once that correction is made, several earlier puzzles become easier to organize. The microwave background can tell us about geometry without fixing the late-time acceleration by itself. A flat model can pass from radiation domination to matter domination and later to dark energy domination. A complete spatial census at one epoch can still require dynamical information before its future is known. The possible fate of the model depends on the physical contents and the fit label, their behavior, not on the curvature content. The distinction is therefore not between a smaller thing called space and a larger thing called universe. It is between one class of information and a fuller cosmological state. Spatial geometry tells us how distances and angles are related at the epochs used to describe the model. Cosmology then adds the contents, their pressures, their initial conditions, and the time evolution that links one epoch to the next. One measured property can therefore be shared while the complete models differ. The shared property can be flat spatial curvature, while the differences can lie in the matter, radiation, dark energy content, and in the histories those ingredients produce. There is no need to make the answer more mysterious than that. In fact, its quietness is part of what makes it useful. A word that sounds like a complete description turns out to be a precise constraint, and once we know exactly what the constraint covers, the rest of the universe becomes easier to ask about. There is one last image that can hold the distinction without turning it back into a definition. Imagine 3 simple graphs drawn on separate pages. Each page carries the same small notation near the top, k=0. The spatial curvature is flat in all 3 models. Under that shared line, however, the curves showing the scale factor against cosmic time take different shapes. On the first page, the radiation-dominated model grows with the square root of time. On the second, the matter-dominated model follows the 2/3 power. On the third, positive lambda drives exponential growth. Nothing about the flat label is wrong on any page. The label never specified that the curves beneath it would be the same. Now imagine replacing those idealized pages with observations. The earliest record is the microwave sky, light released at a cosmic age of about 380,000 years. Its acoustic pattern gives us a ruler tied to the physics of the young plasma, and the angular size of that ruler helps constrain the geometry. The same pattern also carries information about ordinary matter, dark matter, and the initial fluctuations from which later structure grew. Much later in cosmic history, Type Ia supernovae add a different kind of record. Their brightness and redshift trace the distance expansion relation at lower redshifts, and the late 1990s measurements showed that a simple matter-only decelerating picture was not enough. The late expansion was accelerating, and neither observation makes the other unnecessary, because each constrains a different part of the same cosmological history. You can picture the two records arriving in very different forms. The microwave sky appears as a faint wash, nearly the whole sky, almost uniform, until sensitive instruments separate tiny temperature variations by angular scale. A type Ia supernova is brief and local by comparison, a point of light in one distant galaxy that brightens and fades. One carries information from the young plasma, the other from a much later universe, yet both can be placed inside the same set of cosmological equations. That contrast is useful because it prevents the word universe from collapsing into one picture. No single observation contains every epoch. What we have instead is a collection of signals whose travel times and physical origins differ, and the model earns our confidence by connecting them without contradiction. The geometry inferred from the early universe has to live inside a model that also reproduces the later expansion. The matter content inferred from the acoustic peaks has to be compatible with the way structure develops. The component represented by lambda has to fit the distance measurements without breaking the rest of the model. Cosmology becomes a history only when those records can be connected. This gives the question a different emotional shape from the one it had at the beginning. At first, same space sounded as though it ought to mean same universe. The phrase felt almost self-evident because geometry seemed so basic. Once we followed the equations through time, the apparent contradiction dissolved. Curvature can be fundamental to the description while still leaving other physical degrees of freedom undetermined. This kind of answer becomes more precise when we state what the measurement does not determine. A flatness constraint narrows the possibilities, and the surviving possibilities tell us which other observations are needed. The microwave measurement is one of those observations. Supernovae are another. Galaxy clustering, gravitational lensing, and baryon acoustic oscillations add still more ways of testing the same connected history. None of them has to carry the entire universe alone. Each probe also has its own limitations, which is why agreement among them matters. A distance measurement can be sensitive to calibration, a clustering measurement to assumptions about how matter traces the underlying density field, and the microwave background to combinations of parameters that can partially imitate one another. Independent routes through the problem make it harder for one hidden assumption to masquerade as a complete cosmological answer. The important point is not that every probe is equally strong for every parameter. They are useful because their weaknesses and degeneracies point in different directions. A parameter combination that is difficult to separate in the microwave background may be restricted by a late time distance measurement, while structure growth can test whether the same model also produces the observed distribution of matter. Agreement across these different records is what turns a set of parameter values into a coherent history. Even dark energy fits this pattern. The standard lambda CDM model represents the late time acceleration with a cosmological constant, and that is the baseline description used in the model we have followed tonight. The physical nature of dark energy remains unresolved, so the constant description should be treated as a successful model assumption rather than as a microscopic explanation of what dark energy is. That distinction matters most when the equations are extrapolated far beyond the interval we have directly observed. A constant lambda gives a clear mathematical continuation, but the confidence of the extrapolation depends on the assumption that the same equation of state remains valid. The farther into the future the calculation is carried, the more important it becomes to remember which part came from observation and which part came from extending the model. That uncertainty does not undo the answer we already have. It strengthens the reason for phrasing the answer carefully. If dark energy is a true cosmological constant, a flat model can continue accelerating indefinitely. If the effective dark energy behavior is different, the distant future can change even while the spatial curvature remains flat. The geometry alone cannot choose between those possibilities. So when the words space and universe appear together again, the useful question becomes what property we are measuring and how much of the cosmological state that property determines. For spatial curvature, the answer is substantial but incomplete. It tells us how large-scale distances obey the chosen curvature, helps determine how physical rulers project across cosmic distances, and enters the equations governing expansion. But it does not specify the complete inventory of components, their equations of state, or the entire function describing the scale factor through time. Those additional pieces are what allowed our three flat examples to separate from one another. The radiation model, the matter model, and the cosmological constant model were not introduced as claims that three hidden universes exist somewhere beyond observation. They were controlled comparisons, ways of holding one property fixed while changing another, so we could see which part of the physics produced which behavior. The comparison is deliberately modest. We hold the curvature fixed, change the dominant component, and let the equations reveal how the history responds. The same controlled logic appears throughout theoretical physics. A complicated system becomes understandable when one variable is held steady long enough for another variable to reveal what it does. Yes, two cosmological models can share flat spatial curvature while still representing different universes because their contents and expansion histories differ. The word same needs one qualification because the shared property has to be named explicitly. Same curvature class does not mean identical spacetime, identical matter distribution, or identical history. It means one geometric feature matches while other physical features remain free to differ within the equations. That is the distinction the measurements support. It is also why the question does not end with flatness. A future cosmologist could measure curvature more precisely and still have work left to do. A better determination of dark energy could change the expected future without changing the curvature result. A new measurement of matter or radiation could refine the history without altering the basic geometry. A more precise curvature measurement, a better expansion history, and improved constraints on the cosmic contents can therefore refine different parts of the model at the same time. For tonight, though, the important axis is simple enough to leave alone. If some of the details have already begun to blur, the central comparison can survive without them. Flatness tells us something precise about spatial curvature, while the expansion history still depends on the physical components and the way their densities and pressures evolve. Flat curvature can stay fixed while the rest of the cosmological description changes. Picture those 3 pages again, lying side by side. The same flat curvature notation appears near the top of each page. Below it, the 3 scale factor curves move away from one another, slowly at first and then more clearly as cosmic time advances. Nothing dramatic has to happen at the point where they separate. The equations are carrying different physical assumptions forward. One curve bends according to radiation, another according to matter, and another according to lambda. If the labels beneath the curves were removed, the changing slopes would still reveal that the models are not describing the same cosmic history, even though the curvature notation at the top remains unchanged. The picture also keeps the hierarchy of information clear. The notation at the top answers a question about spatial curvature, while the curves below answer a question about evolution. A complete cosmological model needs both layers to agree with observation. Keeping them on the same page without treating them as the same statement is the small conceptual move that resolves the apparent contradiction we began with. Their shared curvature entry stays fixed, while their different physical contents keep writing different futures into the lines below. The small word flat remains in the margin while the 3 histories continue farther apart.